Hi again. In the last tutorial we'll build our SPI modules, the master and the slave, and we saw that they are working. And in the previous tutorial we built our SOC system and we saw how it performed write transaction and read transaction. In this tutorial we'll make the register file that needs to connect the SOC system to the modules, and we'll make the modules for the master and the slave with the register file, so we'll have all the parts for the SOC system. So let's start with the register file. In our Quattros project we'll start a new Verilog file. I'll copy the register file code. This is again an RTL file, so I'll save it in the RTL directory. And let's look at it again. Here are the wires, the inputs and the outputs for the SOC. But here they are other way around. What's output from the SOC is input here, and what's output here is input in the SOC. We have the registers that are going to the master SPI or slave SPI, which is the clock divider, the start and the data in. And we have the wire that come from the master and slave SPI to the register file, which is the busy and the data out. These are for read and these are for write. Okay, now as we said, we have 5 registers and 3 types. Read-write register, which means I write it, I can read it, and it transfers the value to the master. This is the data in and the clock divider. We have a read-only type of register, which is the busy and the data out, which the SPI module generate those values and the CPU can read them. And we have the trigger register, which by writing to it we generate one cycle of trigger which start the transaction. So let's look how they are written. First, the read-write register. This is just the register. When the write is high and the address matches the address we defined for this register, in this case that's data in, which is 8, the write data is written to this register. Very simple. Read-only register are even simpler. The SPI module generate this signal and it's an input to the register file. We just need to upload it to the read data when the address is right. So the 2 read-only registers appear only in this MUX of the read data register, and once the address is right, they appear on the read and the SOC can read them. The trigger register is a little trickier. It looks like the regular read-write register. It goes high, it goes low again. So the only time it goes high is when the write transaction itself is performed. We write it, it rises and it falls back again, and we have one cycle of transaction. That's it. We transfer the outputs from the register to the signals. Now, as you remember, we need here in the transaction, we need a read data valid signal after the read has been performed. So every time we just added this register, reg valid, that gets the read whenever it gets it, and it's come out as data valid, read data valid. The rate request is for advanced use applications. Every transaction is done in one cycle, so we leave it at 0. And actually that's it. That's the register file. Okay, now that we have our register file, we need to build the SPI master and slave modules with the register file. For this we need 2 more files. We'll open another Verilog file and we'll add the master module file, which is the master SPI that we made. We'll save it, of course, first, again in the RTL, because it's another RTL file. And this file is again very simple. It's the file that contains the SPI registers, not master SPI module. Now it has the inputs and the outputs for the register file from the SOC. It has the output of the SPI bus. It has instantiation of the register file and instantiation of the master SPI, and actually that's it. And we need another file, of course, for the slave. The same thing, another Verilog file. Now the slave. Save it again in the RTL directory. And as you can see, it's exactly the same, just that the clock divider signal and the start signal are still in the register file, of course, but they are not connected to the slave SPI because they are not needed here. I left it as a remark just to show you this, but we don't have them here, so they are just unconnected. And it's okay, the optimization of the Quaterus will drop them out. So now we have all the modules that we need. We have the SOC system, the master SPI, and the slave SPI. Like I showed you in the beginning, all the system is ready for integration. We need to go back to our top level file, and we need to add here the full design. We need the SOC and the 2 peripherals. First, the SOC. We have in the test bench that was provided by Altera, we have all the wires needed. We'll leave the clock and the reset for now, and we'll copy them into the wire section. Now we don't need such long names, so we'll remove all the constants, and we need the Nios instantiation. We'll put this in the structure coding. We need to instantiate the 2 SPI modules, the slave and the master, and here we need to make the address decoder. The read command and the write command have to be distinguished if it's a master or a slave. So we check if the base address is 0 for the master, is 1 for the slave, to make it work. Now we also add the address decoder. Now as you can see, the address decoder is very simple. It checks if we're in the master and connect to the input wires of the wait read data and read data valid. It connects the outputs of the wait request, the read data signal, and the read data value of each peripheral, master or slave. And we'll save this. Now we need some more wires. First we need some wires, the clock that we left out from the test bench. We'll add it and connect them. The clock we will connect to the clock of the FPGA, and the reset we will connect to key 0. Now we have to change the values here again. And we change the clock to our clock and the reset to our reset. We still need to add the address decoder wires. And we still need to have the SPI signals and connect them to the pins outside. We'll use the GPIO 0 for the master, S clock, MOSI, MISO, and check select. Make sure that the MISO is an input now here, and we'll use GPIO 1 for the S clock, MOSI, MISO, and SS for the slave. Here the MISO is output. Up till now we didn't synthesize the SOC itself. This is the first time that we actually need to synthesize the SOC itself. Now every time we added a file, it was added for the project, but as you can see in my file list, the SOC is not here, and it's not a Verilog file, it's a special file from Altera, so we need to get it. We go to our file name, we go to the Nios Soc and synthesis, and we need the QIP file. Now actually the first time we finished the platform designer and we go back to our Quartus software, it gives a signal that's saying you need to add this file, but now we just use it for simulation, so it wasn't very important. So now we have to add it. So now we have the full design and we can synthesize it. And it's done. The whole, now we can see in the hierarchy that we have our Nios, our two master and slave, and we have our full design ready to be implemented. But before we implemented it, I want to simulate it with the software for the SPI. This I will do in my next tutorial. Thank you very much.